In this session, we are going to talk about continuous probability distribution. We'll be trying to use majority of these continuous probability distributions in R. So the theoretical concept of it, yes, a little bit we would be covering regarding each of these distribution, but the major focus of it talks about the primary application of each of these distributions and what are the kind of R functions that are available to execute these continuous probability distribution. So that would be the typical focus of this session. So agenda wise, we would talk about the different probability distributions that are supported by the base R package, right? The base R, we are not talking about additional packages here. Different probability distributions that are supported by R. We'll spend some time understanding the normal distribution, which is one of the core distributions for a lot of business applications. Then, apart from normal distribution, there are a few more distributions that are used in hypothesis testing. When I'm saying hypothesis testing, making inferences from the samples, taking the sample data, making some kind of inferences to the population. So there are a few important distributions that will come in handy there. So the primary among them, these are the three: the chi-square distribution, the F distribution, and the student's T distribution. So we would be spending some time understanding each of these three. Then a lot of applications in lot of domains where the data follows different kinds of patterns, and some of the most commonly used patterns again for different kinds of data, one being a gamma distribution. So we'll see how the gamma distribution is different from a normal distribution. So what would be the typical shape of a data which would be following a gamma distribution? Similarly, we would spend some time on exponential distribution, which is otherwise a special case of gamma distribution. We'll talk about it. Then another kind of distribution which my data can follow could be a beta distribution. So we'll try some kind of graphs for all these distributions. How does this distribution typically look like? And similarly, we would be looking at Cauchy distribution. Log normal distribution again has a lot of applications in the real world, especially when I'm working with stock prices and all. I would expect that the stock prices follow a log normal distribution. Then we have some kind of applications related to logistic distribution, Weibull distribution. So these are all univariate distributions, right from gamma distribution to Weibull, along with the ones that are above it. They are all univariate. And we would also try to handle, if at all there are two different variables or two or more variables which are very much interrelated or correlated among them, how do I really handle them? So we will talk about a multivariate normal distribution which has so many applications, because we would be looking at correlations and covariances and various such kind of aspects in the real world. Then a uniform distribution, one of the most simplest of the distribution. So we will look at the uniform distribution. And finally, we would just introduce, if at all my data is not following any of these specific patterns, I want to create my distribution out of the data itself. We are calling it as an empirical cumulative distribution function. So how do we look at all these things is something that we are very much looking at here. Now, so with this, we'll get started with this session. Few important things. All these distributions are nothing but they are the patterns of the data, right? I'm taking the data, I'm looking at a histogram of the data, right? And I'm seeing whether this particular histogram I can map this histogram to a particular theoretical pattern. And all these distributions are simply the theoretical patterns. So if I can more or less map the histogram of my data to a theoretical pattern, I can proceed for further analysis, right? I can draw a lot of inferences because theoretically I know a lot of things about that particular pattern. So I can make lots and lots of inferences by understanding that my data is following this particular pattern. So that's one of the prime reasons every data that we look at, we try to map it to some kind of a pattern so that the next level analysis, whether it is drawing some kind of conclusions or creating some kind of predictions, all these things become more and more handy once I am able to map my data to a particular pattern. So these patterns, they are available. One, if my variable is discrete, we have different kinds of discrete distributions. And if my variable that I'm talking of is continuous, again we have different kinds of distribution. So again, n number of distributions are being theoretically researched and created as patterns for us, so that every data that we are coming across, we could see which pattern is more closely representing our data. And let me tell you that patterns are more like ready-made templates for us. So if our data is following one of those specific patterns, I can understand the attributes of the data more and more effectively, and that is one of the prime reasons, especially if I have to move towards inferential and predictive kind of analytics. I am observing the existing data, trying to map it to a specific pattern or a specific combination of patterns. It could be one single pattern, or I can map it to a combination of patterns. But once I am able to map it, it means I have generalized my data. The way I am getting my data, I'm moving away from exclusively my data to a very general form of a data. And once my data is general, I know how it will come in the future. From how it has come in the past, I will have an understanding of how it will come in future. And because of that, I can make lots and lots of conclusions. Okay, I can make lots and lots of probabilistic comments. I can make lots and lots of inferences by looking at the distribution that it is following, and lot of decision making becomes more and more simpler. So that is where understanding different kinds of distributions come in more and more handy. Now, coming to R, there are good number of distributions that R supports, both in case of discrete as well as in case of continuous. And let me tell you, this session is not explaining the theoretical aspects of each of the distributions in depth. You can very well refer to my other videos on probability, where each and every distribution and the theoretical base of each of these distributions is dealt in depth. But whereas as far as this session is concerned, we are more focused on R. Probably we'll take a data set, we'll see to what extent each of my data is getting replicated through a particular distribution. If I'm trying to map my data to a particular distribution, how would that distribution look like, right? Now, in R, there are, for every distribution, if you see, there are a good number of distributions that R is supporting. A beta distribution, this is a list of both continuous as well as discrete. Beta is a continuous distribution. Binomial is a discrete distribution. Cauchy is again a continuous. Exponential is continuous. Chi-squared is continuous. F is continuous. Gamma is continuous. geometric is discrete, hypergeometric is discrete, log normal is continuous, logistic is continuous, negative binomial is discrete, normal is continuous, Poisson is discrete, sign rank is discrete, and T is continuous, uniform is both in continuous as well as in discrete, Weibull is continuous, and Wilcoxon rank sum is in the discrete case. So these are different kinds of distributions. In this session I am focusing more on the continuous cases itself, but remember these are the R functions. So if I want to understand the beta distribution, the function is beta. If I want to understand the Cauchy distribution, the function is Cauchy. And these are the parameters that it will take as inputs. So when I am talking of beta distribution, I have to give shape 1 and shape 2 as the inputs. Whereas if I am talking of a Cauchy distribution, I have to give location and scale as the inputs. Similarly, if I am talking of F distribution, I have to give degrees of freedom 1 and degrees of freedom 2 as the input. So these are the various parameters that each of these distributions will take. So it is a quick ready reference reckoner for you. Of course, you can very well search the net as well, or you can very well look out for the help file of R as well to talk about what are the inputs that you have to give to each one of them. But much more than that, a few important things for all these distributions. R gives 4 different kinds of functions. The ones that are prefixed with P, they are called cumulative probability functions, right? Which is talking about the probability of a particular random variable taking on a value less than or equal to X. So these are called as cumulative probability functions. Generally, you will find it as an S-shaped curve. So for any value of X, it talks about the probability of obtaining a sample value that is less than or equal to X. I'll try to find out for each value of X, what is the probability that I'll get a sample value less than or equal to X. That is what we get through the cumulative probability. So if for normal distribution, I want cumulative probability, I'll put a P, and for a normal, it is norm. So I'll write it as P norm. P norm, when I'm writing it as a function, and I have to specify the parameters. In case of normal distribution, the parameters are mean and the standard deviation. So I have to give the mean and the standard deviation as the input. I will get the cumulative probability that is associated with this particular mean. So I have to give the X value. Along with that, I have to specify the mean and the standard deviation, which will give me the cumulative probability until that particular value. Then the next function that I can talk about is the D, which means I can use a function called D norm. So prefix it before each and every distribution. Few important points regarding the density function, it's never negative. So when we are talking about a discrete random variable like Poisson, binomial, etc., it's nothing but it's a histogram. So which is talking about the probability of X is equal to X. This is what would be computed when we are going with the D norm. Right, the probabilities are the ones that are typically taken, not the count. So what is the probability that X is equal to X? That is what happens in case of discrete functions, whereas in case of continuous, for every distribution there is something called as a probability density function. So the based on that probability density function, it will find out, which is nothing but it's the derivative of your distribution function. P norm is giving me my cumulative distribution function. The derivative of this cumulative distribution function is the probability density function at this particular value X. So it will try to find out what is the limiting value of this cumulative distribution function at this particular value X. So generally, Okay, if I'm talking about a normal distribution, so there is a kind of cumulative PDF which is 1 by root 2 pi sigma squared e to the power of minus half x minus mu by sigma whole squared. This is the PDF associated with a normal distribution. Now what it will compute is at a particular value x, what is the value of this PDF? This is what is given by the density function, right? It's like individual values that I am generating. Then the third important function that R supports is the quantiles of the distribution. When I say Q norm, I can give, let's say I'm giving it as 95%. So corresponding to this 95% area under the normal curve, let's say the area under this entire curve is 1 unit. I'm talking about 95% of the area under the normal curve. So what is the value? So I'm trying to give a probability, probably you can call it as inverse of this. I'm giving a or probably you can take it as an inverse of this. I'm giving a probability. So here I'm giving the x, and based on x I'm getting the probability. Here I'll give the probability, and based on the probability I'll get the value of x. That is what is arriving at the quantiles of the distribution. So for what value of x, the area under that particular the distribution curve will be 95%. So that is what we are calling as the quantile of that distribution. And the fourth one, which has a prefix of r, which is like r norm, which generates random numbers which is following that particular distribution, so that we can really test out on various things. So this mechanism generates random numbers associated with each of these distribution. So for every discrete, every continuous distribution that R is supporting, you can very well get all these four. One, the cumulative, talking about probability of x less than or equal to x. Density, probability of x equal to x. Then quantiles, finding out x from the probability. And the random numbers, talking about randomly generating a data that is following that particular distribution. So with these as a base, we will get started with the distributions. Probably we'll start with our data set and see to what extent I can map all these data sets to different values of the data set to a particular distribution. So let's get started with the normal distribution, which is one of the most important distributions that we really need to be comfortable with. We have to really get a good hold on the normal distribution if we have to work on parametric statistics. As I have already said earlier, the normal distribution has a probability density function 1 by root 2 pi sigma squared e to the power of minus half x minus mu by sigma whole squared. But in this, again there is a special form called as a standard normal distribution. So if the mean of a distribution is 0 and the standard deviation is 1, standard deviation is 1 means variance also will be equal to 1. So in this case, what is happening here? F of x is nothing but 1 by root 2 pi sigma squared is 1 e to the power of minus half x minus 0 x by 1. So it is becoming x squared. So this is what is typically called as a standard normal distribution. If the probability density function is something like this, 1 by root 2 pi e to the power of minus half z square, this is called as a standard normal distribution, and this one is a very general normal distribution. In all these cases are not just for normal distribution. This is a very universally applicable kind of a concept. If I am trying to plot a probability density function for anything, right? I'm trying to plot the probability density function for anything. I will find that the area under the curve will be equal to 1 itself, not just for normal distribution. For any kind of a distribution, I can very well take it as granted that the area under the curve for any probability density function is going to be is going to be 1 itself. Let's say I want to do a quick plot, right? I want to do a quick plot of a normal distribution in R, right? The data wise, okay, let me use this data later, right? I am taking the price data, stock price data, but let's generate a normal distribution. So I'll take in X, on the x-axis I'll take values which are sequential from, let's say, -3 to +3, -3 to +3 with a gap of 0.01. So I'm taking all these values of X, right? And I will try to find out the densities associated with each of these values. So these are the ones, I'll save them into a variable called P. So let's say I am plotting d norm of X. I am taking the density function of each of these values. X is a value from -3 to +3, and I am taking the density function associated with each one of them. So that is what I am calling it as. Now if you quickly look at creating a plot, right, I'll take a plot of X comma P, and let me say the type is L, so that it is a line plot that I am going with. What I could quickly see, this is a normal curve that is coming out. As simple as this, right? Because I am giving X and I am taking a standard normal distribution here, right? From X is -3 to +3, differing by 0.01. I'm taking, so if you look at X, these are the different values X is taking, right? Because we have separated it by 0.01. And similarly, we have got the different values of P, which is nothing but the d norm of X. And based on that, we are able to plot a normal distribution curve like this. So the d norm is a function that is plotting the probability density function. And now you could see that this particular curve, the area underneath the curve is always equal to 1. And even if my distribution is not a normal, if it is not a standard normal, even if my data is not a standard normal, I can convert it into standard normal by subtracting every observation. From every observation, subtract the mean of it, divide by the standard deviation of it. I'm going to get the standard normal distribution itself. Or the other way of saying, if I have a normal distribution, right, if I am having a d normal distribution, let's say now my X is here by default, when I have used the d norm, my X is my mean is 0 and the standard deviation is 1. But if they are something else, then I have to convert them into normal, and then only I can very well use, we will take a data set and we'll see if this is following a normal kind of a distribution. So let's see, I've taken the price anyhow, I've copied the data. So let me see, let me take the histogram of this change.1, right? Let me take the histogram of, let me attach the price, right? I'm attaching the price. I'll take the histogram of, I'll take the histogram of change.1. So this is how the histogram is coming on the top of it, right? I can increase the number of the bins, but now I really want to see whether this is following a normal distribution or not. So I have to put the probability density function on the top of it. So let's take that up. But what we are simply saying is, initially I'll generate this kind of a histogram, and on the top of it I can try and see whether this particular data is following a normal distribution or not. We can actually put the normal distribution curve on the top of it, right? So let's talk about it. I'll come back to it. And now, okay, let me go back to my normal distribution plot. So this is my normal distribution plot. Now, when I'm using p norm z, right? So this is the z values. So when I'm taking, right, these are the x-axis values are the z values. So when I'm saying p norm of, let's say, -1, when I'm saying p norm, so what is it? Is a cumulative probability distribution. So -1 is this one. So I'll take it, this is the area. So less than or equal to x means these are all the possible values. So it will compute what is the area under the normal distribution curve up to this. So if I am saying p norm of -1, it is saying 15.86%. So which is telling me the area under the left tail corresponding to this -1. So this much area is typically around 0.158%. And similarly, if I want the right tail, I'll simply do 1 minus, because 1 minus of this is the right tail part of it. And similarly, if I want a value between -1 and +1, what is the probability that the value will be between -1 and +1? It's nothing but p norm of 1. I can look at the p norm of 1, which will give me the area from here to here, minus p norm of -1, which will give the area on the other side. So it is saying, so between -1 standard deviation from the mean to +1 standard deviation from the mean, the area is approximately 68.26%. So some of the important and quick calculations that we can make by looking at the normal distribution. And based on this normal distribution, another important theorem also that comes into picture, which is called as a central limit theorem. You take the repeated samples, right? Any distribution, you don't think of it as a normal distribution. Let's say you're talking about an exponential distribution or some random kind of a data. Any kind of a data you take repeated samples from that particular population and calculate their averages, right? Some dummy set of numbers, you calculate their averages. What it says is, these averages will definitely follow a normal distribution. Not the values. Any data you take, any distribution, and from that you take samples of some big size, probably a sample of 100, 200, 500. You keep repeating this experiment n number of times. Take samples of 500, compute the average. Take another sample of 500 from the same data, from the same population. Take another sample of 500 and again compute the average. Another sample of 500, compute the average. Look at the distribution of those averages. Every time the average will change because your sample has changed. But one common property that you will observe with those averages is, the averages, they will be normally distributed. So that is one important property that is associated with the normal distribution. So your raw data can belong to any kind of a pattern, right? The raw data that you are taking could be any kind of a pattern. But if you are trying to find the sample means of that from that raw data, the sample means will definitely follow a normal distribution whose mean is equal to mean of the population with it will be approaching the mean of that population, and whose variance will be equal to the variance of the population divided by the number of samples that you have taken, the sample size that you have taken. So this is what we are calling as the central limit theorem, which is again which because of which we have lots of applications of normal distributions coming in hypothesis testing world. So you can really find that probably we'll do this exercise. We'll check how a uniform distribution becomes a triangular distribution to normal distribution. We'll take one example, right? But let's look at a quick aspect from the data, or probably first let's do this. Then we'll try to map our data to this normal distribution. So let's do one random experiment. So let me call A a variable where I am sampling 1 to 6 a dice, right? Where I am sampling from 1 to 6. I'll take 10,000 values from this particular sample. So 10,000 times I am performing this experiment with a replace equal to true, means the same value can come any number of times. So if you are talking about the histogram of A, it comes out like this. More or less 1, 2, 3, 4, 5, 6, almost all of them are coming more or less in a similar way. So it's better that I take the histogram giving the breaks, right? Probably I'll give the breaks as starting from 0.5 to 6.5. This is a better way to define the breaks so that all of them will come in the middle. So I'm getting, because the values could be between anywhere between 0 to 1, I'm given the breaks as 0.5 to 6.5. You could see that more or less all of them are coming with equal kind of a frequency. I can very well change this frequency to a probability as well, wherein I'll add frequency equal to false. When I say frequency equal to false, the same gets converted into a probability. So this is how I am getting my histogram of A. Then again do the same experiment, let's say with B. Bring out another sample. The same set of sample, another, but assign it to B. Once I have assigned it, now find out the histogram of not just A, take it as A plus B. So this values will lie only between 1.5, the minimum will be 2, so I'll take it from, and maximum will be 12, so I'll take it from 1.5 to 12.5. Now in this case, I could see that the histogram is becoming more like this, which is called as a triangular distribution. Right, you are seeing something like a triangle, so which is what is becoming a triangular distribution. So the summation of two dice is following a triangular distribution. Then you keep going ahead with finding out C, D, E kind of stuff also. So keep adding things, right? You keep along with C, you also add a D, and you also add a E. Now you take the histogram of A plus B plus C plus D plus E. Right? You can increase it to any number of times as well. Okay. So because there are 5 values, the minimum could be 5. So I'll take it from 4.5, and maximum could be 30. So I'll take it as 30.5. So I'll get a histogram more coming like this. You could see that there is a lot of normality that is coming into this particular curve. Now, on this same curve, right, this is a histogram of the data that is coming up. I want to plot the normal distribution curve on the top of it. So if I need the normal distribution curve, I need the mean, because this is not let's say on the same, I want to plot the normal distribution curve, right? So these are the values running from 1 to 30, right? I have these values running from 1 to 30. So I need the normal distribution values associated with each one of them. So I need the mean. So the mean of this particular distribution, it's better that I take it mean of A plus B plus C plus D plus E, which works out to 17.51. Then I'll also take the standard deviation of A plus B plus D plus C, which is 3.87. Now I'll try to generate another graph, right, wherein I'm taking A plus B plus C plus, so I'm taking all the values of A, B, C, D, E. So I will take the X variable. In this case, I'll take the X variable as 1 to 30. So these are the values that are possible. Now Y values, I'll have to take them as denorm. So I'll take that as denorm, where X values, for each of the X value I want a denorm to be computed, wherein the mean is equal to 17.5116 and SD is equal to 3.87, because these are the parameters that I need to give for a normal distribution. I need to give mean and standard deviation. So that is why I am giving these two things. I am taking a denorm for each of the X values from 1 to 30. For each of the X values, I am looking at the X variable, where for each X variable, I want to find the corresponding probability density function. So based on this, I'll take on this same graph, I'll take the lines, I'll do a line plot, X variable comma Y variable. Now this is how the normal distribution plot is coming. I could see that the histogram is more or less following a kind of a normal distribution, right? We could clearly see that the histogram to a large extent is following a normal distribution. We can see an overlapping that is created on the top of it. But going back to your data, we'll go back to our price data, right? I'll look at the head of price. So here the change, I'll take the minimum value and the maximum value. So I'll take minimum of change dot 1 so that I can create the range. So minimum is minus 0.154 and I'm taking the max of change dot 1. I'm creating it, I'm getting it as 0.18. So I'll put it as a range between, so X variable, I'll take it as minus 0.16, right? I'll take it as X variable is from minus 0.16 to 0.19. Let me take this as my X variables, right? Minus 0.16 to 0.19. Then I'll take my Y variables, which is I'll take the denorm. For that I need the mean. So I'll take the mean of change dot 1 and I'll also take the standard deviation of change dot 1. So this is the mean, this is the standard deviation. So I'll get my Y variable, which is nothing but I'll take it as denorm. If I'm assuming that it is a normal distribution, I'll take it as denorm for all my X variables with a mean equal to this much and a standard deviation equal to this much, I want to find my y value. So I'll get the graph associated with this. Then the original data also, it's better that I take it as a histogram, right? So I'll have to consider this as a histogram. I'll first plot the original data in the form of a histogram, wherein I will have to consider the change dot one. If I'm going for a default histogram, it's doing it like this. So I should give the breaks here, right? Change dot one. I'll set it as breaks is equal to sequence minus 0.16 minus 0.16 comma 0.19 comma, we will set it with okay, when I said x variables for different x variables, okay, so we'll put it as 0.01. So if I'm setting it like this, my histogram is coming out more like this. So my x variable also, I can't just set it as minus 0.16 to 0.19. Let me set it as a sequence. Sequence of minus 0.16 to 0.19 increased by 0.01. So this is my x variable. Now I'll compute my y variables with denorm using the x variable. Now let me plot on this graph the lines of x variable comma y variable. So this is my normal distribution. If my data has been a normal distribution here, the histogram, better let me convert it. The histogram, it's better that I convert it from frequency into probability. So I'll set it as frequency equal to false. Okay, I have to put a comma. So this is my, okay, where did I set it? Sorry. I need to go with a histogram. Within this histogram, I'll set frequency equal to false. Okay. When I'm changing frequency equal to false, or let me just say prob equal to true, right? In both the cases, it is showing me the same kind of a graph. So changing from minus 0.5 to 0.5, this is how the typical frequency density function is coming out. Then on the top of it, now I can find out my denorm. So let me now on the top of this histogram, let me plot the denorm, which is the lines of x variable comma y variable. Now if this data is following a normal distribution, the graph of this data should be more like this normal curve, right? Between minus 0.16 to plus 0.19 with a gap of 0.01, my normal distribution curve should be more like this, whereas my actual data is much beyond what is expected if the data is normal. So I could see lot of gaps out here, right? This is not mapping with the lines. I could see so many outliers this side. I could see some outliers here. I could see these are the ones that are having more frequency than what is expected out of a normal, which means it's more highly positively chaotic kind of a distribution. So if I'm trying to see if my data is following a normal distribution, So I'm taking the mean of the data, I'm taking the standard deviation of the data using a denorm function to typically overlap that particular curve on the top of the histogram to see how much it is typically mapping. So for the mean, we will always take from the data, I will compute the mean just like the way I have done right now, and I'll take it as an estimate of the mu. And similarly for the variance, I'll take the variance of the data, I'll take it as an estimate of sigma square. So you could very well take different kinds of distribution functions that are supported by R, P norm, R norm, N, P norm, R norm, Q norm, and D norm. And based on that, you can very well start working with your data, see whether your data is fitting to a particular kind of distribution or not. Here I am seeing when I have taken my change related data, I could clearly see that this change data is no more closely following a normal distribution. I could see lots of deviations of my histogram from the normal distribution, right? So we will try to see if we can fit any other better distribution to this data, but at least at the face of it, the normal distribution is much away for this kind of a data. All right. Now, once we are done with the normal distribution, now we will look at a couple of other important distributions that are used in the world of hypothesis testing. As I have already indicated, hypothesis testing is nothing but I want to make some kind of inferences regarding a population by taking a data from a sample. So there are different kinds of tests, right? We have different kinds of tests associated with making inferences regarding the means of the population, regarding the variances of the population, regarding the proportions of a particular element in a population. So there are different such kind of tests. Almost everything that we calculate can very well be tested. So we have different kinds of distributions that come into picture. Just like the way we have said, sample means they are expected to follow a normal distribution. Similarly, there are a few more things associated with the samples that are assumed to follow some other kind of distribution, and that is where we are looking at chi-square distribution, especially when I am interested in testing something to do with the counts or proportions kind of data, right? I would be using a chi-square distribution. Then we also have F distribution in various aspects of hypothesis testing, especially in an area called analysis of variance, where I am comparing the two variances. I can use an F distribution. Students T distribution is having a lot of importance, especially when I am doing the testing of the means itself, but where the sample sizes are very small. So all these three kinds of distributions, which we would be discussing in our next few minutes, we would be using them in some form or the other as a part of our hypothesis testing process. So what these do is, based on the sample data, we compute what is called as a test statistic. So if I want to compare the variance, I will compute a test statistic. If I want to compare the means, I will compute a test statistic. So for any kind of inferences, I would compute one test statistic. And what we see is this particular test statistic will follow either a F distribution or a T distribution or a chi-square distribution, etc. Now these distributions will define what is called as a critical value based on the parameters of this particular distribution. They will compute what is called as a critical value, and we will always compare our test statistic with a critical value, and based on this comparison our decision is going to lie. So that's how we would be using these three different kinds of tests as a part of our hypothesis testing process. So let's get in trying to understand one by one. So initially, let's get started with a chi-square distribution. At a later point, we would be talking about a gamma distribution whose special case is a chi-square distribution, right? We probably when you look at this, when I talk about the gamma distribution, I will try to bring this density function from the gamma distribution. I'll take the density function PDF of the gamma distribution and make small changes to it to finally arrive at the PDF of the chi-square distribution. So that's where we are calling it as a special case of a gamma distribution. It is having only one single parameter. Even if we have looked at, if I have to give an input in R regarding this gamma distribution, I have to, in normal distribution, we have given two inputs. One is the mean and the other one is the standard deviation. Whereas in a gamma distribution, I have to just give the shape. The shape is the input associated with the gamma distribution. But when we are talking about the Poisson distribution, sorry, when we are talking about the chi-square distribution, for the chi-square distribution, which is the degrees of freedom. The degrees of freedom is one of the most important inputs that I have to give to this chi-square distribution, and the degrees of freedom is nothing but n minus 1, right, which is one lesser than the sample size. If I'm doing it from the sample, mean is equal to the degrees of freedom. If it is following a chi-square distribution, the mean of it should be equal to the degrees of freedom and the variance of it should be equal to twice the degrees of freedom. Wherever I could see this kind of a thing happening, where the mean is equal to the degrees of freedom and the variance is equal to twice the degrees of freedom, then I can very well treat it more like a chi-square distribution itself. And application wise, there are lot many applications that are based on chi-square, right? If I assume Z is following a normal distribution, I could see the summation of all the Z squares Z square will follow a chi-square distribution. So the squares of the normally distributed random variable are assumed to follow a chi-square distribution. That's one of the prime reasons. The sample variance, we said sample means they are expected to follow a normal distribution, but sample variance, which is nothing but like a value minus the mean whole square. So the sample variances, we expect that they follow a chi-square distribution. So that's one more reason why there are lot many applications of the chi-square distribution also as a part of our day-to-day practice. And so when we are trying to compute the sample variance and when I am trying to estimate the sample variance for a data, right, we would typically be using this chi-square test, and it would be used to establish the confidence intervals. Okay, what is the 95% interval for the variance of this particular population? So basically I am taking a sample. Let's say this is my population. Based on this, I have taken some sample of this population. Based on this sample, I have computed the sample variance, and using this sample variance to give an estimate regarding the population variance. So this is what is the activity that I am performing as a part of my chi-square distribution. So what we say is, when we are working with sample n minus 1, which is the sample size minus 1, times s squared divided by sigma squared, is going to follow a chi-square distribution with n minus 1 degrees of freedom. So that is what is the typical understanding out here. So if I have to generate a chi-square distribution, right, in this data itself, all the input that I have to give is the degrees of freedom. So let's try with our data itself, right? Otherwise, let's create first of all a random variables which are following a chi-square distribution. So I require RCHISQ because I'm generating a set of random variables following a chi-square distribution. So if you see what is, how do you give that, right? You can type in question mark RCHISQ. If you look at this part, you have to give it as number, how many quantities you are going to, how many units you are going to generate, and you have to set your degrees of freedom. Only two of the important features. So let me set RCHISQ, right? Let me generate some 1000 units, right? Let me generate some 1000 units, and the degrees of freedom, let's set the degrees of freedom to be around 100. So the mean will be 100, variance will be around 200. So that's how the values would be generated, right? Because if I set the degrees of freedom is 100, we have already talked that the mean will be 100 and the standard deviation is going to be square root of 200 because variance is twice that of 2 nu. So which is variance will be 200 and the standard deviation will be square root of 200, probably around 14. So let's look at generating these values. So we got RCHISQ. These are the values that are associated. So let's save them, right? Rand chi-square. I'm generating that RCHISQ. I'm generating 1000 observations which are having a mean of 100. So now let's do a plot of this, right? So let's take the histogram of this. That should be better. But before that, we require the minimum and the maximum so that we can plot the histogram better. Or let's see the histogram of RAND CHISQ. The histogram of RAND CHISQ is coming more like this. Probably if you increase the number of breaks, that should be much better. So let's set the breaks. So we have the values from 60 to 160, right? So let's set the breaks sequence. Let's start it from 50 and let's go until 170 with breaks of 5 each. That should be sufficient. So now you could see this is how the histogram is getting generated, right? And probably let's take the denorm as well. So x variable will take it as 50 to 170. We'll take it as a sequence from 50 to 170, 50 to 170, and with increments of 5. Y variable will call it as d chi squared. We'll take it as d chi squared, wherein for each x variable I want the corresponding y variable. The degrees of freedom is 100. So these are my y variables. So I can very well plot the line plot on the top of this. So x variable comma y variable. On the same, when I have plotted, okay, my histogram, it's better that I plot it with probability equal to true or frequency equal to false. Now on the top of it, let me plot my lines. So the lines x variable and y variable. So the degrees of freedom are looking much higher, and let me look at what are the y variable here. So for x equal to 50, So 170 x equal to starting from 50 to 170, I am getting my chi-squared values associated with. Okay, so these are the chi-squared values that are coming up associated with each of these. So slightly what you will find is the chi-square distribution is not fully normal kind of a distribution. We'll see some kind of a skewness that is coming up to the right. Probably the best way you can see is the mean of this rand chi-squared. If you are looking at the mean of it is 100, and you are looking at the standard deviation of the rand chi-squared, it is also around 13.94, which is close to. And when we are taking these two things and we are generating the chi-squared value associated with this is the kind of a graph that it is getting generated. So this would be, if you look at the tail, here the tail is slightly more wider compared to this tail. So this is a slightly right skewed kind of a distribution compared to that of a normal distribution, right? Now for the same data, now let me see, when I am going with my chi-square distribution, I really want to see if the price data is following a chi-square distribution. Now chi-squared is appropriate only for the positive quantities. I cannot define the chi-square distribution for negative quantities. So this is where I can very well see whether this close price is following a chi-square distribution, right? So I'll take the close price. Let me take the minimum of close, 0.1. Let me take the maximum of close, 44,000. So let me go with the histogram of close, which is showing a much weird kind of a stuff, right? Histogram of close, I can go with breaks equal to sequence of zero point 0.1 to 44,376 with breaks of 1000 each, right? I'll take something like this and I say frequency is equal to false, so that I will get my probabilities. Okay, breaks do not span the range of x. Okay, so let's set it not from 0.1, set it from 0. We got the minimum value, we got the maximum value. So let's make it 45,000 otherwise. Okay, so these are the breaks that are coming up, and based on this, this is how the histogram got shaped up. Now on the top of it, I want to plot based on my mean. So if I am going with the mean of the close, 467, right? So if I am plotting the chi-square distribution with 467 degrees of freedom, so I'll take x value, x variables as the same, sequence from 0 to 46,000 or 45,000 with breaks of 1000. So these are my x variables. Y variables, I'll take them as d chi-squared, The y variable that I am taking is based on the d chi-squared, wherein I am considering for each of the x variables The degrees of freedom, I'm setting it as 467, right? So based on this, I got my y variables. So I'm plotting my lines x variable comma y variable. So if this data is following a chi-square distribution, the lines of this, which are almost not visible out here, right? Because if you look at the y variables, so these are the values that are associated with the y variables. Probably only one or two of them are showing significant. All other things are coming out to be zeros. So x variable is coming out to be 0, y variables are coming out to be almost negligible, so the graph is not clearly visible at all. So which is making that this data is not following a chi-square distribution in any of the cases, because almost all my values are working out to be zeros when we are talking of this many degrees of freedom. So fair enough. So this particular value is not, this particular data is not following a chi-square distribution in any of the cases. All right. Then let's move on to the next distribution, which is an F distribution, wherein especially we would be using this particular distribution when we are testing the two variances. When I am looking at the sigma 1 squared by sigma 2 squared, it says that this I can very well assess whether sigma 1 squared is more or less similar to sigma 2 squared, or you have a significant difference between the sigma 1 squared and sigma 2 squared. I can very well assess using the F distribution. That's where it is called as a variance ratio test. So the ratio of the treatment of the variances is typically following an F distribution. And when I'm giving it, again, if I can find the critical values, anything, if I want to find the critical value corresponding to a particular distribution, I'll get it through the quantiles of that particular distribution. So QF will give me the critical value associated with the probability function. From my sample, I will compute S1 squared by S2 squared and compare it with the critical value of the F distribution to say whether the samples are more or less uniform, or you find a very significant difference between the variances of the two populations. So the F distribution requires two different degrees of freedom. R is the degrees of freedom for the numerator and S is the degrees of freedom for the denominator. So if I have to find out a quick F distribution, right, we can generate RF. RF dist is what I'm calling rand F. Let me call it as a variable. So for that I'll use RF as a function. And as I said, the F distribution will take two degrees of freedom. So I will select, let's say 1000 values I am generating, and out of which I am saying df1 equal to the first degrees of freedom is let's say 5, and the second degrees of freedom is equal to 10. Based on this, let's say I'm computing my randomly generating values from F distribution. So I'll get a set of values, right? I can very well plot the histogram associated with the random. So it shows, again, this is also a kind of a positively skewed kind of a data. You could see it's a completely positively skewed kind of a data, the F distribution, right? If we are putting a breaks even more clearly, we could see the histogram. I can very well set frequency equal to false, and let me set my breaks. So because the value is ranging anywhere between 0 to, let's say, 20, let me put it as sequence 0, 20.25 each. So you could see that it is completely You could see that these values are completely right skewed. You'll see some abnormal outliers that are shown up here, but majority of it is showing like a right skewed kind of a distribution. So that is what happens with respect to your F distribution. So in some cases, if you really want to model the F, but here the inputs are, we require two different values of degrees of freedom, two different degrees of freedom we require in order to plot your F distribution, right? Now, because of that, if you keep changing the degrees of freedom for the numerator, right? Now it is 5 and 10. Let's say I change the degrees of freedom instead of 5 for the numerator. Let me change the degrees of freedom to 2, right? Let me change the degrees of freedom to 2. I could see now when I am doing the plot of this, I could see that it is completely a kind of a completely a curve that is coming right from the top. It is coming like a downward sloping kind of a curve. But on the other side, if we are seeing, instead of random here itself, let me generate, right, instead of so that we can observe it easily, I'll use the RF function here directly. So let me just take degrees of freedom is just 1. The same histogram, breaks do not open up, right? So degrees of freedom is 2 is fine. Degrees of freedom, let me say it's 4. So when the degrees of freedom is 4, you could see that there is a kind of a hump that is coming up. Here the values are lesser, then the values are going up, and then they are falling. Now you increase the degrees of freedom of the numerator from 4 to 8. You could see that a few of them are on the very small side. You could see a graph that is going up, and from there it is taking a fall. You change the degrees of freedom from 8 to, let's say, 12. You could see, you can even clearly see that the values are going up to here, and from there is a fall that is coming up, which means the shape of the graph is very heavily influenced by the number of degrees of freedom in the numerator. So the shape of the density function of F is purely based on the degrees of freedom in the numerator. And when I am doing the significance assessment here, when I am comparing the two variances, of course we have a separate session on different kinds of classical statistical testing that we are performing. But if I have to do a comparison between the two variances, I'll divide the larger variance by the smaller variance, and significantly different if the ratio is larger than the critical value. So I could very well see the variances, and based on that I could really assess whether it is following a F distribution or not. Then the next important distribution that we are discussing in the same context of hypothesis testing is the T distribution, which is again having this as its density function. We should not bother too much about, but you could see that this is also applicable for data which is lying between minus infinity to plus infinity. When we talked about the chi-square distribution and the F distribution, they are applicable only to the positive values, whereas the T distribution again is applicable to values from minus infinity to plus infinity. It's also a symmetric distribution, but you will find the fatter tails compared to a normal distribution. That's one major difference you could find. All else remaining the same, you will find a significant difference between the T distribution and the normal distribution on those lines. So let's look at a quick plot, right? I want to plot, let's say from x variable, let me take it from minus 3 to plus 3, minus 3 to plus 3 with an increment of 0.1. That's the x variable. The y variable 1 I'll call it as a normal distribution. So I'll take the d norm associated with the x variable. So it will give me the normal distributed. So if I do a plot of x variable comma y variable 1, so it is giving me a normal distribution, right? Now I will call yv2, which is the second variable, right? I could have plotted with a line better. So I'll say this is a line, so type equal to L, and color I'll set it as red. So I'll get a normal distribution plot with a red color. Then let me take yv2, which is purely based on dt. So dt requires the degrees of freedom as one of the inputs. So for every x variable, let me set the degrees of freedom here as just 5. Degrees of freedom as 5. And based on that, let me compare this y variable. So let me plot it as lines associated with x variable comma yv2. So you could see that this is slightly, if you look at this t distribution, this is slightly lesser peaked compared to the normal, but tails are slightly more flatter compared, tails are more fatter compared to that of the normal. So that's the big difference that is being brought out by your t distribution. The same thing if you go with, right, let's create an f distribution called yv3, right, df1 let me set it to 5, df2 also let me set it to 5. Okay, I have to use f, not dt, I'll use df. Okay, so now if I plot lines of x variable comma yv3, now this is how the f distribution starts coming up, right? The range is not sufficient out here, but if so, this is how the f distribution, which is more and more right skewed kind of a distribution, comes up. Right, it's not it's not symmetric like your normal or a t distribution. Similarly, when I say yv4, wherein I am using d chi-square distribution, of course these are defined only for values, positive values of x. That's the reason your f distribution was showing 0 for all the negative values of x, and after that it is showing some kind of a curve like this. The same logic goes with your chi-square distribution as well. So I am taking the x variable, the degrees of freedom I am taking them as 0, 3 or 5, whatever it is. I am taking a degrees of freedom. In case of chi-square distribution, if I take the degrees of freedom as 5, it means the mean is 5, right? So let me take the degrees of freedom as 2, and now if I plot lines x variable comma y variable 2, y variable 4, which is what is the chi-square distribution, even that also will come out as 0 until here. It's also a kind of a right skewed kind of a distribution. So you can think of plotting all the distributions to your particular data, but just a quick comparison between the normal distribution and the t distribution. Both of them are more or less symmetric, but what you find is in case of t distribution, the tails are slightly more flatter compared to that of a normal distribution. And again, if I want to find out the critical value from the t distribution, it's better to use qt, wherein I will specify the quantile below which, so basically giving the probability or the percentage, I have to get that particular value of t, where probability of x value is less than or equal to x. So given the probability, I will find this particular x where probability of x is less than or equal to x. And for all practical purposes, we'll see later when we are doing hypothesis testing, we'll make a quick assumption of t approximately around 2. So these are the three key distributions that play an important role, right? What you need to understand is the shape of the distributions, whether they are symmetric or not, whether you find lot of non-normality in all these distributions or not. So the better way, let's do one thing. Let me generate a t distribution. So I'll do an RT where I'm generating 1000 values, right? This is the best way for you to understand. So rand t is the name of the variable that I'm calling, right? I'm generating using RT, I'm generating 1000 values with a degrees of freedom equal to 5. So around 1000 values are generated which are following a t distribution with degrees of freedom as 5. Let me load the psych package to see the 4 different aspects associated with this t distribution value. Right, we'll look at the skewness and the kurtosis as well. So let me simply put describe, put rand t. What you could see is the skewness of it is 0.5, kurtosis is 2.43. So these are the numbers that are coming out with respect to your t distribution randomly generated values. The mean is coming out very close to 0. Standard deviation is 1.24 for a t distributed value. Right, you will find the minimum is minus 4.46 to maximum is 7.58, and skewness is this much, kurtosis is this much. So let's do R norm. Let's see a normal distribution. I'll call it as rand norm, wherein I am giving R norm as the randomly generated 1000 observations. Let me now do the describe of this rand norm. So what you could see is this is having a mean more or less similar to that of the t distribution, but the standard deviation is 1, whereas here it is 1.24. So I could see that the standard deviation for a t distribution will be much higher compared to that of a normal distribution. Then the minimum is minus 4.7 and maximum is 2.5. So you could see that the range is quite narrower in case of normal distribution. Skewness is more or less closer to 0. Here also it's somewhere closer to 0. Whereas the kurtosis here is just 0.3, which is very close to 0. Whereas in the earlier case, the skewness is the kurtosis is slightly on the higher side, which is an indication of the presence of fatter tails in the data. So that is one more way you could understand the fatness of the tails that are present, but both of them are more or less symmetric. But on the other side, you try comparing the same for the chi-square data that you have generated, R chi-squared. Okay, did we not, we have generated as rand chi-squared, right? Now you could see the mean, because we have generated probably let's generate rand chi-squared also with a mean of we can't generate it with a mean of 0. So anyhow, you see here the kurtosis, if you look at the mean, it is 99.76, standard deviation is 13 points, so which is nothing but square root of 200. Mean is 100, so standard deviation is square root of 200, which is 13 point, which is approximately around this. And you could see skewness is 0.3, kurtosis is 0.18. So here the chi-squared is coming out to be more or less normal. But on the other side, you generate a chi-squared, right? Let me call rand chi-squared, I'm generating 1000 observations with degrees of freedom equal to 4 or 3. R chi-squared, sorry. Rand chi-squared, I'm calling it as a variable where I'm using R chi-squared function, 1000 elements with the degrees of freedom equal to 3. And now when I'm saying describe Rand chi-squared, I'm getting the mean is 3.02 because degrees of freedom is nothing but the mean. Variance is 2 times of this, so variance is 6. Standard deviation will be square root of 6, so this is the standard deviation approximately. Now you could see the skewness is 1.81, so it's a highly skewed positively. Kurtosis is 5.18, which is also indicating that it is highly positively skewed. So what you could see here is, as the degrees of freedom is increasing, you could see that the chi-square distribution is very much approaching a normal distribution in the characteristics. But if the standard if the degrees of freedom is very small, I could clearly see that there is a high level of skewness and kurtosis that is present in the chi-square distribution. So that's how, by looking at all these things, you can do a very good analysis. Similarly, when you are doing a rand f, whatever the random numbers that you have generated through the f distribution, there also you could see skewness is 2.8, but kurtosis is 10.32, which is much higher. So you could see that the f distribution is much more positively skewed compared to your and even the fatter tails are there compared to the normal distribution. So you can very well analyze the shapes of different kinds of distributions using these various functions that are being supported in R. Alright. Now, the next set of distributions that we are looking at, they may not be useful in your sampling distribution, but with respect to the original data set itself, we can see whether our data is following any of these distributions or not. So the first of that kind of distributions we are calling as a gamma distribution. So we are talking about wide range of processes which are positively skewed. In case my data is heavily positively skewed, I can see if I can use a gamma distribution for it. So we have already, let's see the closing price, right? We'll look at the closing price data that we had. So you could see here the skewness of that is 15, kurtosis of that data is 325. So I could see that there is a lot of non-normality that is associated with this data. So they are very heavily positively skewed. So I really want to know if I can go ahead in terms of using the gamma distribution for that particular data. So the parameters for a gamma distribution, we have a shape parameter called alpha and we have a rate parameter called 1 by beta. 1 by beta is called as a rate parameter, alpha is called as a shape parameter. And the density function here is 1 by beta to the power alpha, gamma of alpha is nothing but gamma function. Typically the gamma of alpha, if alpha is an integer, it is nothing but it is alpha minus 1 factorial. Right, because gamma of alpha can be written as alpha minus 1 into gamma of alpha minus 2. So again it becomes, gamma of alpha minus 1. So it becomes alpha minus 1 into alpha minus 2 gamma of alpha minus 2. So if it goes till the last, it becomes alpha minus 1 factorial itself. Now, the special cases that we are talking of is if alpha equal to 1 and we don't touch the beta, then it is called as an exponential distribution, which means 1 by beta to the power alpha. Alpha is 1, so I'll put it as beta. Gamma of 1 is 0 factorial, which is 1. x to the power of alpha minus 1, 1 minus 1, 0, so there is no x term here, e to the power of minus x by beta. 1 by beta into e to the power of minus x by beta is what we call as exponential distribution. So the gamma family of distribution with alpha equal to 1 is called as an exponential distribution. And we have talked about the chi-squared earlier. Wherever I said alpha is nu by 2, nu is the degrees of freedom, beta equal to 2. So it is as good as 1 by 2 to the power of nu by 2, gamma of alpha, gamma of nu by 2, x to the power of alpha by, so nu by 2 minus 1, and e to the power of minus x by 2. So this is what will form the density function that is associated with the chi-square distribution. So these are the two special cases of gamma distribution. When alpha equal to 1, we call it as when alpha equal to 1, we call it as exponential distribution. When alpha equal to nu by 2 and beta equal to 2, we call it as a chi-square distribution with nu degrees of freedom. So I can very well take different kinds of rate shapes, and based on that I can very well plot the gamma distribution. So let's say I want to plot the gamma distribution for different values of x. So let me take gamma is defined only for positive. So let me take x as a sequence from, let's say, 0 or 0.01 to 4 incremented by 0.01. So let me take these as the values of x, and based on these values let me look at different values of gamma. One, I can observe them in one single screen itself. So let me break the screen into 2 by 2. So I'll say par mf rho is c2 comma 2, so that I can observe all four of them in one single screen. Right, so now I'm changing the y values only. So let me do a plotting wherein I'm taking x, the y value I'll take it as d gamma associated with x, and let me take the first I have to give the rate parameter and then the shape parameter. Right, so I'll give the rate parameter as well as the shape parameter. So let's set both of them to 0.5 and 0.5. So taking x, both of them as 0.5 and 0.5, let me plot the first graph. So this is how the gamma 0.5 is coming, right? But let's say if I put gamma 1 comma 1, so this is how the graph is coming, 1 comma 1. Then if I set 2 comma 2, I'm getting a kind of a hump here, right? And if I'm making it 10 comma 10, I'm getting a lot of to some extent a normal kind of a curve, and after that there are lots of extremes that are coming up. But yes, this is useful for modeling almost all the extreme kind of values. You see there's a lot of positive skewness that is getting generated in the curve. For different values of x, different values of this thing are coming out. Now when you are setting this value as 1, it is coming more and more because this is the value of alpha. But if you are setting this value as 10 and set this value as 1, you are getting a completely different kind of a curve. So different values of the shape parameter and the rate parameter. Right, if you are looking at the d gamma, what are the inputs that you are giving? You are first giving the shape parameter and then the rate parameter. the shape parameter is alpha, and then the rate parameter is 1 by beta. And we have said when alpha equal to 1, right, when I said alpha equal to 1, this is becoming an exponential distribution. When alpha is 1, this is becoming an exponential distribution. So that's how we are plotting various values. When alpha is less than 1, we have seen that the function is monotonically declining, right? Almost all the graphs you could see, wherever the alpha was less than 1, we were seeing a kind of a declining function, right? You look at when alpha is 0.5, you will see that it is a kind of a declining function. But when you see that the alpha is greater than 1, we see the humps passing through the origin, right? Let's look at 2 comma 2 or 10 comma 1. We'll see a kind of hump. Probably let's make it 10 comma 10. We'll see a hump that is passing through the horizon, and the degree of skew declines as alpha is increasing. As the alpha is going on increasing and increasing, the degree of skewness is decreasing. That's where I was talking about data coming in more and more normal. You could take a random data as well, right? So we'll talk about describe. We'll generate R gamma. We'll generate 1000 observations with alpha value as 10 and the 1 by beta value as 2. So here comes the skewness is 0.56, kurtosis is 0.28, coming very close to normal. But if the same thing, instead of alpha as 10, let me put alpha is 3. The chi-square, the skewness and the kurtosis are showing much higher. Again, let me decrease the alpha value from 3 to 1. It becomes skewness is much more higher, kurtosis is also very high. And I make this as 0.2 alpha. You see that the skewness is much more higher. But at the same time, you make the alpha as close to 50, you find the skewness and kurtosis are very much close to 0. So making it more and more normal itself. So that's how we could see the skewness keeps changing, because you see the skewness is given by the formula 2 by square root of alpha. If the alpha is right, if the alpha is much higher, you see that the skewness is going lower and lower. The same is going with the kurtosis as well. The mean of the distribution is alpha beta and the variance is alpha beta squared. So based on that, you can assess what should be the value that comes towards the gamma distribution. So if I'm going with my sample again, right, so we'll go ahead with the histogram of the closing price. So let me take again par onto a single screen, mf rho equal to c1 comma 1. Now I am plotting the histogram of the close, where I am saying frequency equal to false, and I am setting the breaks. If I set breaks equal to 100, no, I'll set the sequence itself. So I'll say sequence 0 to 46,000 with increments of let's say 500. So this is how the histogram is coming out, right? With the breaks of 500 is what I am setting as the histograms, and or probably I could set the breaks of 100 only. So I'll set the breaks of 100 like this for the histogram, and now based on this histogram, I really want to see if I can fit a gamma distribution. The mean of it is alpha beta, the variance of it is alpha beta squared, right? So for the data, let me find out the mean. The mean of the data is, I'll take the mean of the close, which is 467, and the variance of the close is 2993232, right? So alpha beta squared is 2.99 million and the mean is this much. So based on that I can say alpha beta squared by alpha beta is nothing but my beta value, right? So the beta value will come out as the variance of this, the variance of this divided by the mean of this will be my beta value, and 1 by of this will be my rate parameter. So the rate parameter I will set it as this much, right? And now, so this is my beta. Beta is 6406. So based on this I can get my alpha value, because alpha beta is this much. So I'll take my alpha value as this divided by beta value. Beta is this much. So I'm getting my alpha value as this. So I can very well try plotting a distribution, a gamma distribution on the top of it. Right, the x variables for me are sequence from 0 to 46,000 with 100 as the interval. Y variables I am taking as d gamma with x variable, and shape is equal to, this is my shape parameter value, and rate is equal to, this is what is my rate parameter value. Based on this I am finding out my y values, and based on this I can very well plot x variable comma y variable. So if it had been a gamma distribution, again this is also a not visible kind of a stuff here, right? The graph got plotted, right? If you want to really check out how this graph is coming out, I'll take a fresh plot of x variable comma y variable rather than as the line. So this is how the plot is coming out, right, where you are having the values almost around 0 only for all these observations. So this is how my plot is coming out. But if I am looking at the histogram, it is showing something different altogether. So my plot is coming out like this, whereas the normal distribute the histogram of the data is coming out more like this. So you don't find that the data is more or less mapping to this particular histogram. We are not sure. Both of them are whether they are more or less similar or not. We'll use later to see how we can compare whether the data is following a particular distribution or not. But because of very less kind of intervals that are operating out here, we are not able to see whether the data is following a particular distribution or not. But on the other side, we have already checked, if we have randomly generated the data from a gamma distribution, how do we really check that particular information? Then the special case of gamma distribution, as I have already mentioned, is an exponential distribution. A lot of applications are there for the exponential distribution. I'm using it in survival analysis. But yes, we will look at the gamma distribution. We have already looked at. We have seen that the skewness and kurtosis wise, as the alpha value is much smaller, you will find the skewness will be much higher. But as the alpha value keeps going up and up, the skewness and the kurtosis levels come much lower and lower in case of gamma distribution. So this is where the gamma distribution will get approximated even to a normal distribution as well. Similarly, exponential distribution is a special case of gamma distribution where alpha equal to 1. So I can very well play around the same way. I could have gone with the gamma distribution itself, keeping my alpha as 1 always, right, keeping my alpha as 1, I can very well play around different values of beta. So now when alpha is 1, beta is 2, these are the skewness. Increase the beta to 3, the skewness is slightly coming down. Increase the beta to 100, skewness is still there. Skewness is increasing. After a certain point, the skewness is increasing. So bring down the beta to, let's say, 5. Skewness is still higher. So that much of skewness is there, positive skewness, with respect to my exponential distribution. Right? Even if I set it to 10, the skewness is there. So you keep changing your data, the skewness of the exponential distribution, it's a positively skewed kind of a distribution. You could clearly see the skewness and kurtosis are slightly on the higher side itself. And when or you can use, instead of doing an R gamma distribution, you could very well generate Rx, right? Probably will generate a small set of values or exponential distribution. Let's say I'll generate only 20 values with the beta value here. The beta, let's say I will set it at 2. So these are the values that are coming up when my beta is 2. And because we have said alpha beta is the mean and alpha beta squared is the variance, and alpha is for the gamma distribution, alpha is 1 here. So if I am talking about an exponential distribution, the mean is beta and the variance is beta squared. So now that I have generated an exponential distribution with these values, the mean of it will be 1 by this. So you look at the mean of, right, this is 1 by beta, the rate parameter. So this is where you could get the mean is very close to 0.5 and the variance is 1 by beta squared, right? So you should get it as 0.5 squared, around 0.25 is the kind of variance it should generate. Of course, the sample size is very small, so that's where you are slightly away from it, but you are very much close to it. Okay, so you can very well use the random generator. You can applications wise, survival analysis uses the exponential distribution heavily, right? Based on when I'm saying here beta, the input is 1 by beta. So the mean is beta. So the reciprocal is what parameters reciprocal is the mean. So if I'm giving something as parameter 2, the reciprocal of it is the mean, which is 1 by 2. So half is the reciprocal period. And I can very well use Rx to randomly generate the values, Dx to match a data to a particular distribution. So just like the graph that we have got when you have used the d gamma function, just by setting alpha equal to 1, when we generate the graphs, we are getting the exponential distribution. Then the next distribution that we are going to look at here is a beta distribution. It requires two positive constants A and B. Right, the input that a beta distribution requires is two positive constants A and B, and this is purely for the x only in the range of 0 to 1. Right, it is not defined for all positive values or all positive as well as negative values. It is defined only if your values are between 0 and 1. It requires two parameters A and B, which are called as the shape parameters, and this is what is the density function gamma of A plus B divided by gamma of A into gamma of B, x to the power of A minus 1, 1 minus x to the power of B minus 1. You could see some kind of resemblance to a binomial distribution kind of stuff, x and 1 minus x. Right, so for modeling the successes and failures, this would be more and more helpful. And this is what is called as a beta function. Gamma of A plus B by gamma of A into gamma of B is otherwise called as a beta function. So we can look at different values of A and B, and based on that we can try different kinds of plots again, right? So because the x is between 0 and 1 only, now I'll take the x values as a sequence between 0, 1 with an increment of, let's say, 0.01. Then I'll take d beta, or probably let me do a 2 by 2 kind of stuff again. mf rho is c2 comma 2. Now I will plot d betas. So I'll take plot of x comma, I'll use d beta. I'll take different values of a and b. Let's say if I'm taking both 1 and 1, the graph that I'm getting is a kind of uniform distribution. This is what we call as uniform distribution. So if my a and b, both of them are 1 and 1, this is the kind of graph that I'm going to get. Now let's see some more things. I set a and b, both of them as 0.5, 0.5. Right, both of them are less than 1. So here there's a lot of meaning with respect to less than ones. Less than 1 versus greater than 1. So both of them are less than 1. I'll get a shape which is more like a U. And you say alpha is less than 1 but beta is greater than 1. You'll get it as a declining function. You said alpha is greater than 1, beta is less than 1. You'll get it as an increasing kind of a function. And you said both of them are greater than 1. You'll get it as inverse kind of a parabola. Now this is how the beta distribution looks like. And if you are talking about randomly generating a few values and then trying to see what are the skewness and all those stuff. So we are talking about R beta, which you have generated using, so let's say we are generating 1000 observations with a mean with alpha value of 0.5 and beta value of 0.5. We could see that skewness is very much around 0, kurtosis is slightly on the negative side. But on the other side, if I make them 2, 2, skewness is very much around 0, but kurtosis is, so you are seeing if both of them are same. On the other side, if you make beta equal to 2, alpha equal to 2 but beta equal to 10, then the skewness is differing altogether. So we can generate different kinds of shapes of the graphs based on the beta, based on the changing the values of a and b for the beta distribution. And a few more interesting aspects here, right? These are the different shapes that are coming out. Fair enough. So we can generate different kinds of graphs looking at the beta distribution. Again, we have different formulas associated with the mean and the variance that are associated with the beta distribution as well. So some basic understanding, right? Beta distribution has a special case called uniform distribution where a and b, both of them are equal to 1. Some of the important aspects that we can very well get through the basic understanding of the beta distribution. Now, moving to the next distribution in this context, which is the Cauchy distribution. It's a long tail distribution, 2 parameters. You'll find it more or less similar to a normal distribution. Inputs wise also it is having a location parameter and a scale parameter. Just like in normal distribution, the location parameter, which is what we are calling as a mean, scale parameter, which is what we have called as a standard deviation. Cauchy distribution also has these two, but unfortunately or slightly differently, we don't call it as a mean, because for a Cauchy distribution, no expected value will exist. For that value, no moments. I can't find the mean, variance, any of them associated with a Cauchy distribution. Real value is, it's a real valued. It's symmetric about a median. Because you can't find out the expected value or the mean here, we are saying it's symmetric more and more about a median. You will find the application of the Cauchy distribution more and more heavily in the Brownian motion, and the general form of the distribution, which is the density function for this, is coming out as 1 by pi b times 1 plus x minus a by b whole square. A is the location parameter, b is the scale parameter. So if a is 0 and b is 1, we call it as a standard Cauchy distribution. So you could clearly see a few things, right? Let's plot a normal distribution. Let's plot a Cauchy distribution, standard Cauchy distribution. We'll see a slight difference. We'll see how these two are differing. Let me take the values of x from minus 3 to plus 3 by 0.01 increment, and the y values, y1 let me call it, so are yn, because I am taking out normal distributed values. So because I am taking them as yn, I'll take them as what do I do? Yn, I'll take it as d norm associated with x, and let me make this 1 by 1 kind of an area, right, instead of 2 by 2. Now let me plot x comma yn normal, and let me plot type equal to line. So this is a normal distribution that I have got. Then let me take yt, the t distribution also I'll bring into the same graph, right? So that's where I'm using a dt, right? And for all values of x, I want the dt with 5 degrees of freedom. So I'll add x variable, which is x comma yt, where I have used the dt function, type equal to line, but let me set color equal to red. So the t distribution is coming in this way. Then I'll also add y Cauchy, right? So I'll use d Cauchy, wherein I am taking for all x, my location parameter a is 0 and my scale parameter b is 1. Unused arguments, okay, d Cauchy. Let me just see how the d Cauchy is defined. Okay, location and scale. I can't give a and b. I have to give them as location and scale. Okay, so tc, I'll say location equal to 0 and scale equal to 1. So I've got my tc here. I'll take my lines x comma tc, right, x comma tc. This also I am taking it as a line graph, and the color of it I am setting it to green. So my Cauchy is coming this much fat tail. You see the green. So the Cauchy is more and more a fat tailed kind of a distribution compared to a normal distribution. So if you are, but it is symmetric again, but it is carrying a much fatter tail compared to a normal distribution. So that's one more point that we have to understand here, right? So for any data, we can think of fitting a Cauchy distribution if you see that the outliers in the data on both the sides are extremely high. Alright. Now, the next distribution that we are looking at in this context is a log normal distribution. Log normal distribution takes values on the positive real line. So it is defined only for the positive numbers. But one important property of a log normal distribution is if I take the logarithm of the logarithm of the data will be normally distributed. Right? If I'm taking the data as it is, if it is log normal, if x is following a log normal distribution, I say that the log x will follow a normal distribution. That is what is the property associated with a log normal distribution. Lots of applications in the real world, especially the stock prices, they are expected to follow a log normal distribution. So we can use again L norm is the function that is associated with the log normal. So I can use the density function, the cumulative distribution function, the quantile function, as well as the random number generator. So the log normal distribution will have a mean of e power mu plus sigma squared by 2. Here the parameters are again mu and sigma, but the mean of it is e to the power of mu plus sigma squared by 2, whereas the variance of it is e to the power of sigma squared minus 1 into e to the power of 2 mu plus sigma squared. That's how the log normal distribution will be seen. So again we can plot the log normal distribution. You will find that it is extremely long tail and it is a very heavily positive skewed kind of a distribution. If you really want to see that, well, let me take the values of x, right? Let me take the values of x from 0 to 10. Okay, let me take it from 0 to 10 with a gaps of 0.05. This is my values of x. Then I want to plot my y. So I'll compute my y as d log normal for x, right? I have to give the two values, the mu value and the sigma value. So if you see the way you define dl norm, you will define it with mean log equal to something, sd log equal to something. So you are giving a mean and the standard deviation in this way. So let's set the y dl norm of x. So you'll set the mean log equal to 0 and sd log equal to 1. If I'm setting something like this, now if I plot x comma y, so this is the way the log normal distribution is coming out, right? You will find it very much right skewed kind of a distribution, right? You can change the y values to whatever extent you want. Let's say you are changing it the mean value to 10, and then you are doing a plotting of x and y. In this case it's coming out more like this. So you are finding it too much of skew that is present in the data, right? The mean log, and based on the standard deviation of the log values, you could get the mean log is mu value, the sd log is the sigma value, but the mean and the variance of your distribution could be something else. So if we are talking about our particular data following a log normal kind of a distribution, then I have to look at computing the mean log and the standard deviation of the log based on this formula, right? So e power mu plus sigma squared by 2 will be the mean of the data. Whatever I am taking, the mean of the data will be equivalent to this. Variance, if you are looking at it, e to the power of sigma squared minus 1, and this part e to the power of 2 mu plus sigma squared, I can write it as mean squared. So mean squared is equal to this much, mean squared times e to the power of sigma squared minus 1 will be the variance. So mean squared, so based on this, once I know e to the power of sigma squared minus 1, I can compute it as variance by mean squared, and from here I'll get e to the power of sigma squared is 1 plus variance by mean squared, and sigma squared will come out as logarithm of this, so which means sigma will come out as square root of logarithm of 1 plus variance by mean squared. So that is how I'll get my SD log value, and based on that I can very well simplify finding out the mean value as well. So that's how I'll find out the mean log and SD log, and based on that I'll try to map my data to a particular distribution. So that's how I can work with log normal distribution. But generally when my data is extremely long tail and having too much of positive skewness, so for this you can just see the describe. Let's generate a random numbers RL norm. Let's say I'm generating 1000 values with mean log of 0 and SD log of 1. Right, when I look at the describe, I'm seeing skewness is 5.3 and kurtosis is 49.3. So that's the level, and that too when I'm increasing the mean, in that case I could see that the skewness is 4.4, kurtosis is 32, especially when my skewness and kurtosis are much higher, then I can try to map the data to log normal distribution. The logarithm of that particular data will come closer and closer to a normal distribution. Probably if you are seeing the same describe, right, if I am taking the logarithm of these values, right, I'm just taking the logarithm of these values, suddenly you see that the skewness and kurtosis levels are very close to 0, which is a clear indication that this data is coming closer and closer to normal distribution. The logarithm of the data which is log normally distributed will result in a normal distribution itself. Then one more distribution which we really need to understand in the context of the data analysis is the logistic distribution. So at later point we'll be discussing more and more about it, but it is one of the important distributions, especially in the generalized linear modeling, which we'll be taking up later. Especially the errors are binomial in nature. So it's a link function. So we'll use it very heavily in a mechanism called binary logistic regression, right, where we are trying to model yes no kind of situations or a categorical variable with two different outcomes. So in those kind of thing, this is a very important link function that will help us in terms of modeling this aspect. So at that point we will discuss more and more about it. But application wise, especially where I'm trying to create generalized linear models with binomial errors, I can rely on the logistic distribution. So lots of analysis associated with the proportion related data, right? What percentage of people are defaulting versus what percentage of the people will not default. If I have to look at such kind of information, then logistic distribution comes in more and more handy. The cumulative probability distribution, which is nothing but P logis. The cumulative distribution function is always an S-shape. Generally, all the cumulative distribution functions will be more or less S-shape, and they are all bounded by 0 and 1. So this is how the equation will typically come out for a logistic distribution. And the logarithm, when I am taking the logarithm of P by 1 minus P, this is the basis for Q is nothing but 1 minus P. So when I am taking the logarithm of probability of occurrence of an event divided by the non-occurrence of an event, it follows a linear distribution of the form A plus Bx. This is one of the prime reasons It is used for modeling the probability of an occurrence of an event vis-a-vis the non-occurrence of an event. So that's where for binary logistic regression, the logistic distribution comes in more and more handy. It's also a unimodal symmetric distribution. Again, the tails of this distribution are also slightly longer than that of the normal distribution. For the same thing, all else remaining the same, compared to your normal distribution, we are talking about a log normal, a logistic kind of a distribution. You'll find that the tails will be more and more wider. So let's try comparing both of them. So x, again, let me take the values between -5 and 5 with 0.01 as a gap. Yn, I'll call it as a log, as a normal. So let me call it as denorm of x I'm taking. So let me plot yx comma yn, and type, let me call it as L, so that I'll get a line graph. So this is a normal distributed curve. Now on the top of it, I want to plot a logistic regression. So I'll take YL delogis for the x values. That's it. Let me plot now YL lines x comma YL type equal to L, but let me put the color also to differentiate. Color equal to red. I'll use the, so you could see that it is much lesser peaked and the tails are much flatter associated with the logistic regression. So logistic regression will have such kind of a distribution compared to a normal distribution. You will find that the tails are much fatter compared to that of a normal distribution in case of logistic distribution. So it is very well used to model the growth curves, wherein the rate of growth is proportional to the amount that is already grown and the amount that is still expected to be grown, right? Because we are talking of logarithm of p by 1 minus p. So the probability, the rate that is already grown, so it is like developed versus to be developed. So for modeling these kind of growth curves, like after a certain point of time, there will be a kind of a saturation in the growth. So if I have to model those kind of things, I cannot use a regular normal distribution kind of an equation. So this is where logistic distribution comes in more and more handy. And you could see that in case of logistic distribution, the tails are slightly more fatter compared to that of a normal distribution. Then comes the next important distribution, which is a Weibull distribution, right? This is primarily for this purpose. If I'm talking about R links in a chain of data, and we are talking about the strength of each of the link, right? The correlation, the strengths of each of the links are independently distributed. I want to look at the distribution of the weakest link. We say that the distribution of the weakest link will approach a Weibull distribution. And again, it has two parameters. And the special case of a Weibull distribution is again an exponential. So here also you could link the exponential distribution. So which means from gamma somewhere you are coming to the exponential distribution. Even a Weibull is leading you to the exponential distribution. And as a business application, it is used very heavily for modeling your death rates in survivals. Lot of actuarial models use a Weibull distribution, right? Because the death rate can increase with age or decrease with age when I'm using the Weibull distribution. It's not one single, depending on the parameters that I'm providing, depending on this alpha parameter, I could see that the death rate can decrease with age or increase with age or stay constant with age. That's the important characteristic associated with a Weibull distribution, and that's one of the prime reasons Weibull distribution is used heavily for modeling the death rates. Survival analysis, there is a heavy usage of Weibull distribution. And you will find that the mean of this is 1 by alpha times mu, variance of this is this much. But majorly, if you see, alpha and lambda are the two important functions, two important parameters associated with the Weibull distribution. So we can actually generate, if you look at the data, we can very well generate a Weibull distribution with different sets of values alpha and lambda, so that we can understand how the data is changing heavily in case of a Weibull distribution. So we can use different kinds of alphas, right? As I said, if alpha equal to 1, it means that it is an exponential distribution, because if you see alpha equal to 1, it comes out as lambda, this part is nothing, t to the power of 0, which is 1, and e to the power of minus lambda t. So lambda is nothing but, if I take it as 1 by beta, it becomes more and more similar to that of your exponential distribution itself. So when you say alpha equal to 1, it becomes an exponential distribution, and in the application side we call it as a hazard is constant. If alpha is greater than 1, we take it as hazard is increasing with age. Less than 1, we say that the hazard is decreasing with age. So let's take different values of alpha and lambda. Right, we can very well take different values of alpha and lambda, and we can use the d Weibull function, which is more generated using the Weibull distribution. I'll use Weibull. So d Weibull is the function that I'm going to use. So let me take the x values from 0 to 2, sequence 0 to 2, increment by 0.01. Then I can very well use y, which is nothing but the Weibull. So I'll use d Weibull. I'll take for each value of x. I want to give the alpha value and the beta values. Sorry, alpha and lambda. So I have to define how I should define the alpha. So let me put d Weibull shape and scale. Right, shape and scale. So scale is, I can very well set the scale as 1, but the shape, so let me take the y as d Weibull x, right, and shape, let me take it as 0.5, and scale, let me take it as 1. So I got my d Weibull values, and I'll take the plot of x comma y. So this is how, if my shape is 0.5, this is how my Weibull distribution is going to come. But if the shape is changed from, let's say, 0.5 to 1, so this is a kind of a declining hazard function. If the shape is 1, then it becomes a constant hazard function. Almost you will find it as a constant kind of a stuff. But on the same lines, if I am setting my shape as a much bigger value, let's say I'm setting my shape as 3, and now I'm doing my plot of x and y, I get it more and more a kind of a normal kind of a distribution, right? Even if you are looking at the skewness as well, let's look at the describe, wherein r Weibull, right, wherein I'm setting 1000 values, where I'm setting the shape equal to let's say 0.5, and scale I'm setting it as 1. So skewness and kurtosis are much higher here. Whereas on the other side, if I set the shape as 1, exponential is also a highly skewed kind of a distribution itself. But if you see, when my shape is 1, you will find that the skewness and kurtosis have come down very much. Now if the shape is increasing to 2, the skewness and kurtosis have come even more further. And shape is becoming 3, you could see that it is almost approximating to a normal distribution itself. So this is one more place where you can see by changing the shape and by changing the shape parameter, I can very well think of my Weibull distribution also getting approximated to a normal distribution, right? So that's one more understanding that we need to have regarding the normal distribution. Next, once we have an understanding of all these single variable univariate kind of distribution, one more important point just I want to bring in this session is the multivariate normal distribution. We are talking about two different vectors of normal distribution, right? This data will follow a normal distribution, this data will follow a normal distribution, and the correlation between them also will be intact. So that is what we are calling as a multivariate normal distribution. So this data will follow a normal distribution, this data will follow a normal distribution, the correlation between these values also will be intact. And to execute that, we would be relying on MVR norm, multivariate random normal distribution values from the mass library. So I have to load a library called mass. If it is not there, you have to install the same. And then I'll use an MVR norm which will generate the random numbers. But here I have to specify the means. I have to specify the means of both the variables. So let's say I'm having two random variables, right? Let me talk about MVR norm where I'm generating two different set of random numbers. Let me take them into XY, right? I'll take MVR norm where I'm generating two sets of two different variables X and Y, both of them following a normal distribution independently but maintaining a correlation between them. So I'll generate 1000 such pairs where the means of the first one is 1 and the mean of the second one is 2. So I'm generating such kind of a data. And even if I'm looking at the variance covariance matrix between them, so I have to give a variance covariance matrix. It goes like this because there are if there are two variables, I'll generate a 2 by 2 matrix, which is here it will show me the variance of the first one, here it would be the variance of the second one, here I'll have the covariance between 1 and 2, here I'll have the covariance between 2 and 1. So the way I give is these four values I give, first, second, third, fourth. These are the four values that I'll give as inputs. The second and the third one should be the same because they are the covariances in both the sides. So I can very well set as a matrix. So I'll set the variance of the first one is 2. The covariance between the first and the second is 3. The covariance between the second and third is 3. The variance of the fourth, the variance of the second one, let's say, is 5. Which cannot be, which is very much possible. So let me take this as the matrix. And because I have to make it as a 2 by 2 matrix, I say number of rows equal to 2. So I have created this as a matrix and I'm generating xy. So my xy's got generated. Now you could see here the variance of xy. If you see, you'll get the variance covariance matrix. The variance of the first one is coming out to be approximately 2 because they are random numbers that got generated. The variance of the second one is getting approximated to 5. The covariance between them is getting approximated to 3. So this is the data that you have got. Now you break the data, right? You take both, if you look at head of xy, it will give me in pairs, the first one and the second one. So this is the first one, this is the second one. So I could take x separately, wherein I am saying xy. Out of this xy, I am taking all the rows and taking only the first column, calling it as x. In y also, I am taking xy, taking all the rows and only the second column. So I'm getting my x and y. I'll get the mean of x. I'm getting the mean of x as 1.03. So this is what I have given the mean as, first one as 1. I'll take the mean of y, getting it approximately 2. This is what I have given as input. And I could also find out the covariance between x and y. So which is 2.82, which is very much close to 3. That is what we have defined. We'll get variance of x, we'll get variance of y. So variance of x is close to 2, variance of y is close to 5. All these things are typically coming out. And when you find that the correlation also you can find, which is nothing but covariance divided by the standard deviation of both of them. So you can set correlation of x comma y is around 0.94 because covariance is nothing but, correlation is nothing but covariance divided by the product of the standard deviations of both x and y. So this is how you can analyze a multivariate normal distribution. We can extract, first we can generate the data which is following a multivariate distribution with different parameters. You can extract them into separate vectors and plot them to look at the correlation. You look at the variances. If they are independent, you will find that the variance of the sum should be equal to sum of the variances. So variance of x plus y is 12.2, variance of x is 1.8, variance of y is 4.7. So the summation of these two is not equal to this, and in fact variance of x plus y is much higher than variance of x plus variance of y. Similarly, if you take variance of x minus y also, it is 0.96. So you are finding variance of x plus y is greater than variance of x plus variance of y. Variance of x minus y is less than variance of y minus variance of x. So because that is what indicates that the variables are not independent. The higher is the difference that is existing between the variance of the summation and the variance of the difference, I could see that the correlation between them is much higher. When the variance of the sum is equal to the variance of the difference, it means that the covariance or the correlation between them is literally not existing. I can make a conclusion with respect to their independence between the variables. So those are some of the important things when we are working with two or more variables. Multivariate normal distribution will have its own play. Uniform distribution, we have already discussed about it. Application wise, it is used very heavily in the random number generation, right? All R's that we are talking of, they are the random numbers only. And in a lot of applications with respect to random number generation will depend on the uniform distribution. And it's a special case of the beta distribution, right, where the A and B are set equal to 1. And in many cases, even after exploring the data in depth, we may not be able to map our data to any one of the available distribution. We may have to create our own empirical distribution. So in that case, we can very well use this ECDF as a formula, which will create the empirical cumulative distribution function for our data. So if you say in this case, I'll say ECDF associated with what is that? What are the variables that we had? Let me just bring in the price, names of price. So I have changed dot one, right? So what I can very well do is I can look at ECDF associated with change dot one, right? This is the kind of ECDF that I am getting, wherein you could see empirical cumulative distribution function right from -15 minus 0.15 to 0.18. It has created the ECDF. Now what you can very well do is you can do the plot of ECDF of change.1, which will tell you the typical graph of how this is like. So up to here it is on the 0, the probabilities are more or less 0, slowly started rising up, and from there it is going more flatter. You could see that it's more or less looking symmetric. So you could very well say that on the lower side versus on the higher side, not too much of difference in the skewness is cropping up. But at the same time, if you say ECDF, if you look at the plotting of ECDF associated with the closing price, you'll find that it's a straight up, and after that again it is very much flat. So all the values, majority of the values are in this range itself, and after that it's going to be much flatter. And if you are finding that LHS is more steeper than the RHS, so here it is very steep. So if the LHS is more steeper compared to the RHS, you will find that the data is more positively skewed. Otherwise, it is more and more negatively skewed. So you can very well plot your own data itself, empirical cumulative distribution function of the data, and probably use that kind of a distribution at a later point for making some kind of conclusions or inferences out of the data. So these are a lot. These are different kinds of distribution functions that we have tried to understand, especially the continuous probability functions. Right, all these distributions. This is just an overview, understanding the main features, how their shapes look like, which of them are more stable in shape, which of them by changing the values their shapes are going to change, which of them are symmetric, which of them are positively skewed. We can very well see all these kinds of distributions and get a hold on them, because at a later point when we are observing our data, depending on whether they are very highly positively skewed or very symmetric kind of stuff, we would try to choose an appropriate distribution for our data for doing further calculations on the same. All right, I hope you got a good amount of understanding, good amount of comfort level in terms of working with or getting a basic hold of different kinds of continuous probability distribution. If you have any further queries on the same, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@basegurus.com. Thanks a lot for listening to this session. Thank you very much.